OCR Chemistry A 5.3.1 Ligands and Complex Ions. Using Chemistry Explained means participating by writing notes and completing the tasks with a pen on paper or on a tablet. Pause and replay the slides at the pace that suits you. Most importantly, when prompted, pause the lesson, thinking a problem through, taking your time, completing the task before continuing and correcting your work. So we'll start with a general description of the chemistry of complex ions, move on to types of ligands, bidentate, monodentate, and then the occurrence of stereoisomerism in complex ions. One of the set of distinctive properties of the transition metals is the forming of complexes and complex ions. A complex comprises a central metal atom or ion bonded to a number of ligands. If the complex is charged, then of course it is called a complex ion. You'll see the formulae written employing a square bracket. So this is the hexa aqua ion 2 FeH2O6 square bracket 2 plus. Ligands are molecules or ions able to donate a lone pair of electrons. That means they're able to form a dative covalent bond to the central metal ion. So here's our water molecule acting as a ligand. A lone pair is donated to the central metal ion. In this context, this dative covalent bond is called a coordinate bond and will be referred to as such throughout this lesson. The number of coordinate bonds between the central metal ion and the ligands in the complex is called the coordination number of the metal ion. So if we look at the hexa aqua ion 2 complex, we'll see that there are 6 water molecules surrounding the central metal ion, and therefore 6 coordinate bonds have been formed, so the coordination number of the ion 2 plus ion is 6. We can also determine the shape around the central metal ion using valence shell electron pair repulsion theory, shapes of molecule theory. Now, if you need to review that, please refer to an earlier lesson. The shape we would predict from that is octahedral. So we have a square planar arrangement for 4 of the water molecules, 1 above and 1 below. We determine that because there are 6 bond pairs, 1, 2, 3, 4, 5, 6, which get as far apart as possible. The name for that shape is octahedral, as mentioned, and the bond angles 90 and 180. So the bond angles here, of course, are 90, but the bond angles between these 2 bonds, well, that's where the 180 comes into play. So within the octahedral, there are 2 bond angles to take note of, and that has some relevance later in the lesson. The majority of complex ions that we'll meet at A-level have a coordination number of 6. So if we look at another example, it's an iron 3 cyanocomplex, and please note we don't include in the specification the naming of complex ions, so I won't go through the correct chemical name for this complex. However, we'll see that once again we've got 6 ligands. So we would expect a shape around the central metal ion, an octahedral arrangement of the cyanide ions. How do we account for the 3 minus charge on the complex? Well, it's very simple. The complex ion charge is the sum of the charges in the complex. So we know that as it's ion 3, that the charge on the ion is 3+. We know that each cyanide ion has a 1- charge, so there's 6 of those, so a total of 6 negatives, 3 positives and 6 negatives. The overall charge on the complex is 3-, and that's written as a superscript to the right of the bracket. We also generally include the charge, as far as A-level exams are concerned, it's highly advisable to do so on any displayed diagram. So a couple of simple exercises. Deduce the charge X on each of these iron 2 complexes. So we know that in each case it's an Fe2+ ion, Fe2+ ion. Pause. Calculate the overall complex charge. Come back to check your answer. Okay, so I'm going to go through the reasoning and reveal the answers. So Fe, the ion here, is at 2+ ion. Ammonia is a neutral molecule, so we've got 6 neutral molecules and 1 Fe2+ ion. Therefore, the overall charge on the complex is 2+. Now here, we've got +2 for the ion, and we've got 2 times -1 for the hydroxide ions, and of course, the water molecules are neutral. So we've got +2 and neutral, 4 neutral molecules and 2 times -1. So there's no charge on that particular complex. Okay, so let's move on to a different type of problem. Deduce the oxidation state of the metal in the complex ion. So we've got chromium, 3 ammonias, chromium and 6 ammonias in a 3+ complex. What must be the oxidation state of the chromium, and similarly for the copper? Pause, work it out, come back. Okay, so, well, as the ammonia molecule is neutral, the 3+ charge on the complex ion must be due to the charge on the chromium. So the chromium oxidation state is +3. For the copper chloro complex below, we've got 4 times -1. These are chloride ions. Copper must be +2 because the overall charge is 2-. So that comes to -4 or 4-. So +2, 4- comes to -2. So the copper must have an oxidation state of +2. +2 for the copper, 4 times -1 for each chloride ion comes to +2 for copper. Earlier we stated that the most common coordination number for metal within a complex was 6, but there are a small number of complexes that have a coordination number of 4. They show 4-fold coordination. These often include tetrachloro complexes, as we saw on the previous slides. There were 2 examples there. So let's look at them again. Here's a tetrachloro complex of copper, and here's a tetrachloro complex for cobalt. Referring to the valence shell electron pair repulsion theory, decide on the geometry and the bond angles around the central metal ion. Come back to check against mine. Okay, so to reveal, so the copper central, we've got 4 chloride ions, so I'm taking this, the tetrachloro, as my model. It's exactly the same argument for the cobalt. So 4 chlorines, 4 bond pairs will arrange themselves tetrahedrally. So we've got 4 chloride ions, I should have said, each donating a lone pair of electrons to form a coordinate bond. So there are 4 bond pairs. So that will arrange tetrahedrally. And the bond angle in a tetrahedron is 109.5. Now, there's a little subgroup within the transition metals, platinum, nickel, palladium, which often form 4-fold coordination complexes, but unusually, these complexes may show square planar geometry. So this does not follow valence shell electron pair repulsion theory and has to be known as anomalous. So unusually, they show square planar geometry. So here are 2 examples, a platinum ammonia complex and a nickel cyanide or cyano complex. The geometry is a square planar arrangement. So we've got, for instance, for the nickel, we've got central nickel, 4 cyanide ions. Nickel is at 2+, I deduce, because the overall charge is 2-. So that's representing a square planar geometry. What are the bond angles? Pause, think it through. What are the bond angles? Come back when you have your answer. Okay, so we've got a square planar arrangement with bond angles of 90. So here, the angle between those 2 bonds and any bonds within the square adjacent bonds is 90, but the bond angle between the bonds that are opposite each other, that's obviously 180. So that again may have some relevance later on in the lesson. Bidentate ligands. Ligands may be able to form more than 1 coordinate bond to the central metal ion. Those that do form 1 coordinate bond by donating 1 lone pair are known as monodentate ligands. The ligands we've met so far in the lesson are water, monodentate, ammonia, chloride ions, hydroxide ions, all monodentate. A model central metal ion, here's water, a lone pair donated. Notice it isn't that water doesn't have, or oxygen has 1 lone pair, it has 2 lone pairs, but only one of them is suitable to be donated to form a coordinate bond, and that is to do with orientation. On the other hand, bidentate ligands are able to donate 2 lone pairs to the central metal ion to form 2 coordinate bonds. The standard bidentate ligands at A level are 1,2-diaminoethane and the ethane dioate ion, and we'll meet those on the next slide. So starting with 1,2-diaminoethane, for which I have written the formula, and here is its structure drawn in a way that allows it to form 2 coordinate bonds with a central copper ion. So I'm taking a copper complex as my model. The lone pair on nitrogen donated to form a coordinate bond. Lone pair on nitrogen. So the 2 lone pairs are in different parts of the molecule, which allows them to be positioned to meet the requirement for octahedral geometry. You'll see in textbooks and A-level questions, rather than writing out this whole structure, a focus just on the atom that donates the lone pair of electrons. So the nitrogen of the diamino compound, the second nitrogen of the diamino compound, and some structure in between. So we'll see again a lone pair of electrons donated, two coordinate bonds formed by the one molecule, and then we have a third bidentate ligand to allow for 1, 2, 3, 4, 5, 6 coordinate bonds around the central metal ion, which I haven't written it down, it's actually a copper 2+ ion. So knowing that that's a copper 2+ ion, pause, write the chemical formula for the complex ion. These are representations of 1,2-diaminoethane, and also determine the coordination number of the central copper ion. Pause, come back when you're ready. Okay, so the formula, copper, 3 1,2-diaminoethanes. 1,2-diaminoethane is a neutral molecule, so if copper, as I stated earlier, is a 2+ ion, then the overall complex is 2+. Now here's an important thing, the coordination number is 6. It's the number of coordinate bonds. So you've got 3 bidentate ligands, each forming 2 coordinate bonds, so there are 6 coordinate bonds. The coordination number is 6. So let's move on to the ethane dioate ion, which we can write as like so. And we can represent it structurally. These are negative charges like so. Complete the diagram for the copper ethane dioate complex. Write its formula and determine the coordination number. If you're not clear, it follows the pattern for 1,2-diaminoethane. Pause, come back when you're ready. Okay, so to reveal, and by the way, you are expected to draw these complex ions, so you do need to practice them. Each lone pair on the oxygen of the carboxylate groups forms a coordinate bond. We can represent 2 other ethane dioate ions with a focus on the oxygen, the lone pair containing particle or atom, and a line representing the rest of the structure. So again, we have a formula where we've got copper, 3 ethane dioate ions, each at 2-, copper's at 2+. So the overall ion charge is 4-. The coordination number is 6. 1, 2, 3, 4, 5, 6 bonds. I recommend some practice questions at this point. If you have the OCR endorsed textbook available to you, you will find some suitable questions on page 408. Summary questions 1, 2, and 3. Complete them and check the answers on page 581. Of course, other textbooks will also have suitable questions. Stereoisomerism in complex ions. Stereoisomers have the same molecular and structural formula, but a different arrangement in 3-dimensional space. You will have met cis-trans, EZ, and optical isomerism. We're going to start with the occurrence of cis-trans isomerism in complexes with a metal coordination number of 4 and a square planar geometry. The example from the specification is the complex platin, which is a platinum ammonia chloride complex. Here is its representation in the square planar form. Decide whether that is cis or trans. Pause and decide. Okay, so that is indeed the cis isomer. That is, the chloride ions are on the same side of the structure. Platinum being the central ion, chloride ions on the same side of the platinum. If that is the cis isomer, pause and draw the trans isomer. Okay, so to reveal the trans isomer, we have the chlorides on opposite sides of the platinum. A key point to note is that the bond angle between the chlorine-platinum platinum-chlorine bond, that bond angle is 90 in the cis isomer, but the chlorine-platinum platinum-chlorine bond in the trans isomer has a bond angle of 180. Cisplatin is an effective cancer treatment drug. It binds to the DNA of the cancerous cell, disrupting the replication process. However, there are some harmful side effects, including kidney damage. Please note, transplatin has no such effect. This is an example of stereospecificity. Cisplatin has a drug action, transplatin does not, and that is very common in drug therapies. Cis-trans isomerism is also shown in octahedral complexes where there are 4 of one type of monodentate ligand and 2 of another type of monodentate ligand. The standard A-level example is a cobalt-3 complex involving 4 ammonias and 2 chloride ions. If I show you the cis structure, or one representation of it, we'll see that we have the chlorides on the same side of the cobalt. That is, the chlorine-cobalt bond angle, the chlorine-cobalt-cobalt-chlorine bond angle is 90. You may see that in different orientations that are achieved by rotation. If this is the cis structure, pause and draw the trans structure. Come back to check when you are ready. Okay, so to reveal, here we have the trans structure. I'm just going to point out that the chlorine-cobalt-cobalt-chlorine bond there is 180. So you may see what's distinctive, I should say, of the trans is that the chlorine-cobalt-cobalt-chlorine bond angle is 180. You will see that represented as different rotations. So that is cis-trans isomerism, where we have 4 of one monodentate ligand and 2 of another. We also can see cis-trans isomerism where we have some bidentate ligands. So a complex which shows this cis-trans isomerism involves cobalt and 2 1,2-diaminoethane ligands and 2 chloride ligands. The trans structure can be drawn as shown. So here we have the 1,2-diaminoethane, and this is the second one. And here are our 2 chlorines on opposite sides of the cobalt above and below the plane of the square planar structure. Okay, pause and draw the cis isomer. Come back when you're ready. Okay, so to reveal the cis isomer, so we have the chlorines with a bond angle of 90 between them, and here the chlorines have a bond angle of 180. So trans 180, cis in these octahedral arrangements indicated by a bond angle of 90. So we can say that chlorines are on the same side, whereas in the trans, the chlorines are on opposite sides of the cobalt. Let's move on to optical isomerism. Now, optical isomers have opposite effects on plane polarized light. And it's shown by molecules that are non-superimposable mirror images of each other. That phrase has to be produced exactly as written, non-superimposable mirror images. We can form non-superimposable mirror images with complexes that have 3 bidentate ligands. For instance, cobalt 3 with 3 1,2-diaminoethane ligands, bidentate ligands. Here is a representation of the complex central cobalt, focusing on the nitrogens which donate the lone pair of electrons. We've got 3 bidentate ligands. Pause, carefully draw a mirror image of that structure. Come back to see how you've done. Okay, so to reveal, so this nitrogen matches up, this nitrogen matches up, this nitrogen matches up, this nitrogen matches here, and this nitrogen matches here. So we have these two joined, we have these two joined, and we have these two joined. So we've drawn mirror images of the two. They are optical isomers. That is, if you try and pick up this molecule and place it on top of this molecule, you'll see that the orientation of the ligands is different. You cannot get an exact match. Rotation will not allow you to do that. So these are non-superimposable mirror images, and therefore they have opposite effects on plane polarized light. They are optical isomers. Working from exactly the same complex, but this time looking at a model kit, which you may or may not have done in class. So here's one bidentate ligand, here's another bidentate ligand, here's another bidentate ligand. Here is the mirror image, here is the plane of the mirror. It's easier to visualize looking at this model kit that if I pick up the right hand model, rotate it so that the red bidentate ligands match in terms of their space, you'll see that the blue bidentate ligand and the yellow bidentate ligands will not be in the same orientation across the two molecules. They are not identical. Complexes with 2 bidentate and 2 other monodentate ligands may also show optical isomerism. So if we return to the cobalt complex we met when we were doing cis-trans isomerism, so it's cobalt 2 bidentate ligands, 1,2-diaminoethane, and 2 chloride ligands, and we look at the cis isomer. Now the cis isomer I represent or reproduce here. So we've got the chlorines with a bond angle of 90 on the same side of the molecule or same side of the structure. Pause. Carefully draw the mirror image. This is required at A level. Come back to check. Okay, so I'm going to reveal. So I've matched up the positions of the chlorines. I've got an imaginary mirror plane of the mirror down the middle of my page here. So the nitrogens match up, the chlorines at the top, the nitrogens at the bottom, and then on the far side, nitrogens and nitrogens. So these links, these bidentate ligands match up. So these are mirror images. If you rotate this right-hand structure so that the positions of the chlorines rotate by 90 degrees, so the positions of the chlorines match, you'll see the orientation of the bidentate ligands is different. They are non-superimposable mirror images. So this particular complex shows both cis-trans isomerism and optical isomerism in the cis isomer. The trans isomer does not show optical isomerism, but I'll stick with the positive. The cis isomer does. Some suitable practice questions at this point would be the OCR endorsed textbook, if it is available, page 412, questions 1, 2 and 3. The answers are on 582. Of course, other textbooks will also have suitable questions. If necessary, go through this lesson once again. That's your decision. Complete some practice questions from any suitable textbook before moving on to the next topic. That next topic is your choice. Any feedback you'd like to give me, I'm available at that email address. Thank you very much.